Welcome viewers, the LPTEL lecture series on the calculus of variations. This is the fifth lecture of the series. In the last lecture, we discussed the concept of surface integral, where surface B is in 3-dimension space x, y, z, and a function is defined on the surface, that is f x, y, z for each point P which is whose coordinates are x, y, z. This point is on the surface and the values of this function are defined on all points on the surface and on its boundary. B is the surface and delta B is its boundary. This function is assumed to be continuous on the surface and on its boundary also. So, then the surface integral, double integral over B f x y z d s, this is capital S and not the arc length small s. Here d s is the element area on the surface. The typical surface element is like this shaded darkened curved square or curved rectangle. This surface is partitioned into these element areas ds delta s1, delta s2 and so on up to delta sn, and xi, yi, zi is a point in this delta si. Then the integral is defined as the limit of this sum, summation I equal to 1 to capital N, when n is the number of these element surface areas, the number of elements partitioning the whole surface, and then we take this summation f of x I, y I, z I, where x I, y I, z I is the point in that element area delta si times the area of that element, that is delta si, and if this limit exists, we define it as the integral double integral over B f x y z d s. Here this integral will be defined. It will not be depending on the way we partition it. For any partition, when we pass to the limit, it should give you the same value. So, under the sufficient conditions like f is continuous and this surface is piecewise smooth and its boundary is piecewise continuously differentiable, then this limit does not depend in the manner we partition it, and so the integral will be defined. Here, how we calculate this surface area? We, as we know, we have some experience of calculating on the flat planes the functions which are defined in certain domain like this. So, here x in the x y plane we have this flat surface area d and a function z is defined on this, and we have seen that the surface area is given by this formula. This also is a particular case of the more general one which we are going to consider. So, here we have for any point P on this surface like this. Here the surface is parameterized by two parameters u and v. So, a position vector of a point P, that is the directed vector O P starting from O and ending at P. So, here it will have three components x, y, z. So, each component is a function of u v, those parameters, and so we get x u v, y u v, z u v, like that. These are the components. So, the vector r will be given by x u v I plus y u comma v j plus z u comma v k, and these u v are within the range of these bounded intervals alpha, beta and gamma, delta. So, here then this element area d s, we have seen that this comes out to be the cross absolute value of the cross product r u cross r v d u d v, because r u d u is the tangent on the curve v equal to constant, and r v d v is the tangent element on the curve u equal to constant. So, this curved surface element like this darkened one will be actually given by which is d s equal to absolute value of the cross product r u cross r v, and since d u d v is positive it comes out. So, that is the element area d s, and so here r u is the partial derivative with respect to the parameter u, and r v is the partial derivative of r position vector with respect to v. So, each component gets differentiated partially with respect to those variables, and we get this. And so, r u cross r v square, here we use the formula which we proved that for any two vectors a and b in R 3, we see that a cross b is given by absolute value of a cross b square is given by absolute value of a square times absolute value of b square minus a dot b. This is the dot product of two vectors, that is a 1 b 1 a 2 b 2 a 3 b 3, where a i's and b i's are the components of a and b respectively, the square of that. So, we get this r u cross r v absolute value square like this, and so this r u dot r u is E, that is how we define that r u dot r u is E, and r v dot r v, this is F, and r u dot r v, this is G. So, this absolute value of r u cross r v square comes out to be E f minus G square. So, therefore, absolute value of r u cross r v is square root of E f minus G square. We take here positive square root, and that is what we have here. And so, our formula here this integral comes out to be in terms of, now these are x y u x y z are functions of u v here, and this we have calculated that d s equal to square root E f minus G square d u d v. So, that is nothing but this integration over the flat surface d u d v, which we already know how to calculate. So, that is the surface integral formula in terms of parametric representation u v, and then also we have normal derivative, general normal derivative in 3 dimension. As we have defined the normal derivative of any function here. So, we have some surface here like this, and some function phi is defined on this. So, phi x y z, which is defined at each point on this surface. So, normal derivative of this phi is, so normal derivative of phi, which was defined like we defined it in 2 dimension, we define it limit of delta n tending to 0 of phi x y z minus phi x prime y prime z prime. Here this is a part of the surface, the closed surface like this, where here this is x dash y dash z dash inside the domain, and the point x y z is on the surface. So, here it is assumed that phi is defined at those interior points x dash y dash z dash. So, this limit over delta n, and we, as before we have seen it in 2 dimension, it turns out to be gradient of phi dot n cap. So, where n cap is the unit normal, this n cap is the unit normal, which is n 1 I plus n 2 j plus n 3 k. I j k are unit vectors in x y z directions respectively. and we see that this unit vector, therefore, n 1 square plus n 2 square plus n 3 square, this should be equal to 1. These are direction cosines, they are also given like this. If this normal makes this angle alpha, beta and gamma. So, here it is like I will blow it up in this way, this with x axis, x, y and z. So, with this z the angle is gamma, with this x axis alpha and this beta. So, n 1 is actually cos alpha, n 2 is cos beta, n 3 is cos gamma, where this n cap is the unit vector. Here there is a normal to the surface and it makes angles alpha, beta, gamma with the coordinate axis, and so these are the direction cosines given by cos alpha, cos beta, cos gamma. So, we can see that this can be calculated, and so this is also the another notation of this is del phi over del n. So, we can see that del phi over del n is del phi over del x. Gradient vector is del phi over del x, and then first component is n 1. So, that is cos alpha plus del phi over del y cos beta plus del phi over del z cos gamma. So, this is another convenient formula for this. If in terms of direction ratios, we have certain numbers here, small a, small b, small c, then we divide by its square root, summation a square plus b square plus c square. So, that is also can be seen here. If let us say the surface, if the surface is given by z equal to some function of z x y, then we know that the normal. So, in that or in terms of u x y z, let us say if we give u x y z equal to some constant c, if we can solve it for z explicitly, we can express this z as a function of x y also. So, then we know that the normal will be gradient of u over. So, this in this case then n cap comes out to be gradient of u over absolute value of the gradient of u, and then we get the directional derivative. So, del phi over del n is we have gradient of phi dot n cap. So, that will be gradient of phi dot gradient of u over gradient of u. So, this in component form, this is del phi by del x, del u by del x plus del phi by del y, del u by del y plus del phi by del z, del u by del z over square with plus minus sign square root here del u by del x square plus del u by del y square plus del u by del z square. So, plus sign or minus sign we have to see that which side we are going to take. So, that cosine of the angle should be positive there, and so that we have to choose either plus sign or minus sign accordingly. If we choose plus sign, if del u by del phi by del n is positive, then we choose plus sign, and if this is negative, then we choose minus sign. Now, here the Laplacian will be defined, Laplace operator or Laplacian is actually defined as the Laplacian of for twice continuously differentiable function we define this Laplacian that of u contains function u. We define Laplacian of u as del 2 u by del x 2 plus del 2 u by del y 2 plus del 2 u by del z 2, which is nothing but gradient of del dot del like this of u, or in short it is written like del square u. That is another notation for the Laplacian. Now, we go to Green's theorem in higher dimension. Firstly, we have seen that Green's theorem in higher dimension. Now, we will see so recall in 2 dimension we had seen that this, if you have this case like in x y you have some certain domain like this, and here this boundary of this is let us say C, and its positive direction is taken like this anti-clockwise. And here we have seen that if m and n are smooth functions, here we see that this m dx plus n dy, this was equal to over d n x minus m y dx dy. This we had established in the earlier lectures, that where m and n are continuously differentiable in D, and they are continuous on piecewise continuous on the boundary, and C is piecewise smooth, then we have this result, which is Green's theorem in 2 dimension. Now, we can generalize this in higher dimension. So, first let us see certain applications in 2 dimension itself. So, we can write this in a slightly different form like this. So, if we take m equal to like this, so we can write this as n equal to p, let us say n equal to p and m equal to minus q. Then we get p dy minus q dx, and this line integral will be then equal to over d, we get p x plus q y dx dy. So, just removing this minus sign from here, and then that minus sign will come here. Now, we can so this is a slide, just same form with different choices of m and n. So, now we take p equal to some eta g and q equal to eta f. Here these eta g and f, they are continuously differentiable functions, and on D, and continuous piecewise continuous on the boundary of D, that is on C, and C is of course assumed to be piecewise smooth. That means, at each point the tangent is well defined, tangent and normal are defined except at finitely many points. So, there so putting these p and q here, you get the following, which is on this side we get eta. So, put this p equal to eta g. So, we get eta g dy minus f dx equal to here. So, we will have two terms here, this double integral, because there are two functions here. So, x derivative will give you eta g x plus eta x g. So, like that we have, and collecting these things here, we get this eta g x plus f y dx dy. Here these are all partial derivative, subscripted means the partial derivative, plus double integral over d eta. So, g eta x plus f eta y dx dy. And so, we take one term on the other side. So, we will get like this here. Okay. So, we have, so we can write this over d like this, g eta x plus f eta y dx dy. We take this on the other side, so we get minus d eta g x plus f y dx dy plus this boundary integral eta g dy minus f dx. So, this is the general form of integration by parts. So, Green's theorem gives us the general way of the same formula which we had in one dimension. Recall that integration by parts formula was a to b u v prime dx is minus u prime v dx plus a to b, and u v evaluated at a to b. So, this is one dimensional. So, this is one dimensional integration by parts, and so this is two dimensional integration by parts. So, this is a generalization of the earlier integration by parts formula which we discussed. Here we can see that here the x derivatives they are on eta, y derivatives they are on eta, and g and f are not having any derivatives here. So, if we shift these derivatives on g, we get a minus sign here like we got here. So, we got minus sign and eta becomes free of derivatives, and this x derivative gets shifted on to g. Similarly, y derivative gets shifted on to f like this, and this eta becomes free of any derivative. We gain minus sign here. So, this is the generalization of integration by parts formula of one dimension. So, this is two dimensional integration by parts formula. Similarly, we can have higher dimensional integration by parts formula. So, we can repeat this process like this. If we take, so take now eta equal to psi and g equal to phi x and f equal to phi y. So, here in this we will take eta equal to psi and g equal to phi x and f equal to phi y. So, we get this thing here, and here these x derivative will give you g x x like that. So, we get finally psi del square phi dx dy equal to minus, this is phi x psi x plus phi y psi y dx dy plus boundary integral psi del phi by del n ds. Here this s is the arc length. So, here we see that here if we put eta equal to psi here and g equal to phi x and f equal to phi y, we get from this here we get g x will give you phi x x and this will give you phi y y. So, that is the Laplacian, two dimensional Laplacian here. So, eta equal to psi and you get Laplacian there, and then in this term here we get g equal to phi x. So, this is eta x means psi x and f is phi y and eta y is psi y. So, we get this term here with minus sign. This can also be written slightly differently like this. And this is the dot product of the gradient of phi dot gradient of psi. And here this is obviously this is we know that this is gradient of phi dot n cap ds. So, this is the in a vector form we have this, and if we interchange phi and psi, we get phi here and del square psi dx dy. This remains the same because it is symmetric. So, we get gradient of psi dot gradient of phi dx dy plus over c. So, psi here this will be phi now and this will be psi dot n cap ds. So, subtracting this we get the following Green's identity, that phi this we can subtract from this. So, phi del square psi minus psi del square phi dx dy, these two terms cancel each other, and so we get this boundary integral phi. We either write like this or we can write del phi over del n form also. So, this is phi del psi by del n minus psi del phi by del n. So, this is Green's one of the Green's identities expressed like this, and if we write phi equal to psi here, we can see that then we will have here del square this dot product will give you square of this thing. So, if we write phi equal to psi in this, if we write phi equal to psi, so we will have in this phi del square phi dx dy will be minus d mod del phi square plus phi del phi by del n ds. So, there are various forms of identities obtained like this, which can be by proper choice of m and n, or in f and g we can see various forms of Green's identities. We can go to higher order integration by parts also. If we take, so if we take this q equal to 0 and p equal to g phi x minus g eta x minus eta g x, then we get, so we substitute here P equal to g eta x minus eta g x and q equal to 0 here. So, we will get the following thing, integration over d, we get g del 2 eta by del x 2 now dx dy, and this is over d eta del 2 g over del x 2 dx dy plus the boundary integral c over c g eta x minus eta g x dy. Because we have chosen q equal to 0 here, q equal to 0. So, we get only, see, we have taken q equal to 0 here. So, this term will not be there, this we will have only p dy, and p is chosen like this g eta x minus eta g x. So, we get the same thing here, and we get, so this is what is now higher order, I mean higher order derivative integration by parts here, because now two derivatives are being shifted on g here. This eta x x, we can write it like this also in short form, g eta x x dx dy. This is over d eta g x x dx dy and plus g eta x minus eta g x dy. So, here this x x, first we shift one derivative, we gain 1 minus sign, and then again we shift x derivative, we get those x x derivatives on g, and eta becomes free. So, this is shifting of derivatives here, because of two derivatives are being shifted, we get plus sign here, and on the boundary we get this term. So, that is the integration by parts formula for second order derivatives. Similarly, we can take now p equal to something and q equal to 0. So, then we will have p equal to g eta y minus eta g y by 2 and q equal to g eta x minus eta g x by 2. So, then we get for mixed integrals, mixed derivatives, that is eta x y dx dy. So, this is now these derivatives are shifted on to this. So, eta becomes free and g x y dx dy over d, and you get those bounded terms 1 by 2 c g eta y minus eta g y dy plus 1 by minus sign here, minus 1 by 2 g eta x minus eta g x. So, this is for the mixed derivative. Now, we go to 3 dimension case, and we will have the following result. So, here we use the divergence theorem, which is what it says here, this for given any bounded volume V here and F. So, here divergence means del dot here, del dot F dx dy dz is actually equal to the surface integral over the surface of this V F dot n cap ds. Here we have the following picture. So, certain bounded volume V is enclosed by the surface S. So, this surface is S. So, at any point the outward normal is given by n cap as usual, and the points are there in the domain in V. So, this is what is the divergence theorem. In component form we get this. So, F has components F 1, F 2, F 3, F 1 I plus F 2 j plus F 3 k. So, then we get here F 1 del F 1 over del x plus del F 2 over del y plus del F 3 over del z. That is the divergence of F, because del operator is del x I plus del y j plus del z k. So, dot product gives you this dx dy dz. Here f these components f i's are assumed to be continuously differentiable in V and continuous on the surface S, and S is piecewise smooth, that is on those patches where S is smooth and is well defined, that is continuous function at every point except on certain boundary of those patches, like it could be like this. So, in these patches let us say S 1, S 2, S 3 and S 4, this n is continuously defined on those patches as soon as. So, here this side, this surface integral side, you get F 1 n 1 plus F 2 n 2 plus, sorry, these are scalars components n 2 plus F 3 n 3 ds. Here n cap as usual have components n 1 I plus n 2 j plus n 3 k. This is unit normal. So, those are defined, those cosines, direction cosines of the normal here. So, how do we see this theorem? Here we will component wise we show that this integral of this del f 1 over del x is f 1 n 1 ds and so on. So, we show, let us do it for the last term. So, last term we will show that this over V del f 3 over del z dx dy dz equal to this over S, this is f 3 n 3 ds. So, like that we have. So, or in what we have to show that like this, that f I, this I equal to 1, 2, 3. So, we show it for I equal to 3. So, what we will have this we again we will do it for a simple case like this, that here we will take this surface as parameterized by the x y here coordinates, and so this surface S is projected on to this R here, this is the projection of this, and let us say surface is like this. We take the simple case that surface has two parts, the upper part, the lower part we write it as z equal to g x y, and the upper part z equal to h x y. So, assuming that the surface can be represented like this, and this R is the projection of this surface, here this is the projection of this, and so R is the projection of projections of both the parts. Let us say this is S 1 and this is part is S 2. So, S is S 1 union S 2. So, then we can see that this triple integral over V del f 3 over del z dx dy dz here will be like this over R, and then here z component will be g x y to h x y of del f 3 over del z dz and dx dy, and so it will be over R here f 3. So, z differentiation and integration will cancel each other. So, we will get the bounded terms x y and h x y minus f evaluated at x y g x y dx dy. So, here we can see that this is what we will see that this is actually equal to the right hand side of that. So, here we see that if we write this parametric representation like this x y. So, then the for the upper surface we see that R comes out for any point P here, position vector R will be given by x I plus y j plus z component is there x on S 2 h x y k, and so this element area here will be, so d s here will be R x cross R y absolute value dx dy, and we can see that this is nothing but, so R x, so absolute value of the determinant like I j k, and here you have 1, R x is 1 and this is 0, and this is h x here and 0 1 h y here, absolute value of that. So, we get here minus h x I. So, let us absolute value of that minus h x I minus g h y j and plus k. So, here this square root of 1 plus h x square plus h y square, that is what we will get here. And so, here we see that this is the here normal, this cos gamma will be positive, and on the lower part we will see that here we get, so this side is nothing but the s of f 3 dot n 3 ds. We have seen that here, let us first see that what is this actually element area. See here, so n 3 ds, this is the vector form of this element area will be actually equal to n 3 is k, ds will come out to be simply dx dy. So, you will have this n 3 ds will be like this, because the component n 3 component is just 1 here. So, n 3 component is the k here. So, we get this. Now, on the lower part we get n 3 ds on S 1, we get this as minus, because here you will have
in the negative direction. So, we will get minus k dx dy. So, we can see that here this you get minus sign on this. So, we get finally the same thing here f x y. So, this dot product n 3 will be 1 here, n 3 will be n 3 is a k component. So, its absolute value will be plus 1 here, and here you because of this you will get minus. So, this minus sign will be adjusted, and so let us say this is 1. So, we get from this integral surface is f 3 n 3 ds as f x y. On the lower S has the union S 1 S 2. So, on S 2 we get positive 1. So, that is h x y. So, let us first do like this. This is S 1 union S 2. So, f 3 n 3 ds. So, first on S 2, that is with positive sign f x y h x y and dx dy, because dot product here will have this 1, and so dx dy and over this region R minus over the region R again, and f 3 x y g x y dx dy. So, we see that it matches with the quantity here for each I. Similarly, we can do for other components, and so we get overall by adding all the terms we get the divergence theorem. Now, so here in the component form it can be written like this, as you have seen already. So, in component form we have this, that over triple integral v we get f x plus f y plus f z dx dy dz, we get over this s f 1, that is, or we can write it in cosine form, cos alpha plus f 2 cos beta plus f 3 cos gamma ds, where n 1 is cos alpha as usual, n 2 is cos beta, n 3 is cos gamma. N has components n 1 I plus n 2 j plus n 3 k. So, we have this. Now, if we choose as before, we choose f 1, sorry, this was f 1, f 1 x, f 2, the components f 3 y. So, f 1, f 2, f 3. Let me write it neatly. This is f 1 x plus f 2 y plus f 3 z. That is the divergence of f here, and so we get this from the divergence theorem. Now, if we choose f 1 equal to, let us say, eta f, f 2 equal to eta g plus f 3 sorry comma f 3 equal to eta h, where again eta f g and h are assumed to be sufficiently smooth, and so we get this over v here f eta x plus g eta y plus h eta z dx dy dz, and we get one more term here. We take it on the other side with the minus sign now, and so we will have over v eta f x plus g x plus g y plus h z dx dy dz. Now, that boundary term is now surface here. So, we get surface integral over the surface S eta, and then you have f cos alpha plus g cos beta plus h cos gamma ds. So, you can see that this is now 3-dimensional integration by parts. Here derivatives on eta. So, here eta x, eta y, eta z. Now, we shift these derivatives on f, g and h, we get this minus sign here, and so we get f x plus g y plus h x here, and eta becomes free of derivatives, and here this is the boundary term, here boundary is the surface. So, we get this, and if we put eta equal to, take eta equal to psi and f equal to phi x, g equal to phi y and h equal to phi z, we get this higher order integration by parts. So, psi del square phi dx dy dz minus, here this is gradient of phi dot gradient of psi. This will have 3 components here, phi x, phi y, phi z, gradient of psi dx dy dz, and plus this bounded term over S psi del phi by del n, which is now 3-dimensional normal derivative ds. If we interchange phi and psi and then subtract, we get the similar formula which we had earlier. So, this over v phi del square psi minus psi del square phi dx dy dz will be, this term will cancel and we will have only the bounded term phi del psi by del n minus psi del phi by del n ds. So, it is a more general form of Green's theorem, which is actually consequence of the divergence theorem. So, with these preliminaries, whatever things are required, we have discussed here in all these lectures. Next time on, we will actually start the our lectures on the calculus of variation. We will introduce certain concepts again, and then we will start the Euler's conditions and various concepts related to the calculus of variations. Thank you very much for viewing the lecture.